behavior models. That is the next step or the next stage in the design, system design. We have already discussed the top-down design process, and we said that we start with the abstraction of the system that we are going to build. That is abstraction because it simply represents the essential characteristics of the system. It does not specify physical realization. We usually use some standardized or accepted language in abstraction. They are called models. Here's the learning objectives of the lesson. At the end, you should have a familiarity with the modeling tools, including state diagrams, flowcharts, and UML, Unified Modeling Language. You should be able to conduct analysis and design with the models and understand how to apply these models to your design project or for any given design problem. Okay, as I said earlier, models, an abstraction of a system, and we can think of as a design specification, and they are quite ideal to describe the functionality of a system at all levels of details, and they may have different intentions for describing behavior system. And they may encourage innovation and provide clear documentation in the design process. Modeling is simply informative representation of a system, process, or an object. That is a standardized representation of a system. It simply captures some essential details without specifying the physical realization of the system. We have modeling language, and we usually use some graphical symbols, some words, letters, modeling language. Typically, models have object type, relationship type, and intention. Object type is simply encapsulating the actual components that we're going to use to construct the target system. Relationship type, how objects are related to each other. And intention, somehow every object have an intention to describe what is gonna do. Okay, the first modeling language that we are gonna talk about, state diagrams. State diagrams describe behavior of a system with memory. So if there is a memory in the system, then we may use state diagram. There are two symbols, state and transition, as we have shown here. State is a rounded rectangle, so it's denoted by a rounded rectangle. And transition is simply an arrow. We have some spatial circles. And final state. State sometimes found to be synonymous with memory, and the state and transition concept, the inputs are associated with transitions between the states and represents the net effect of all previous inputs to the system. So somehow it corresponds to an operating mode of a system. Here we have an example. That's a candy vending machine. We may come across in malls and in other places. We simply deposit some coins, and if we deposited enough with the threshold, we simply get a candy. So here there are, as you can see, 5 cents and 10 cents in this candy machine. Seems to give a candy if we deposited 25 cents per quarter. Nickel and dime are the words are common in US to represent 5 cents and 10 cents respectively. So in Turkish, we can say 5 cents, 10 cents, or 5 kuruş, 10 kuruş. Initially, the system is in reset mode. There is nothing deposited, and that's the initial state represented by a circle, black circle. When we deposit a nickel, then there could be 2 different prices. We can either deposit dime in nickel. If this nickel, then we can get 10 more, and then it's going to be 15. So we simply construct this diagram, and at the end, there should be a decision somehow. Here we have to deposit 25 cents to get the candy. If it exceeds this number, then we simply get a candy. Otherwise, it goes to the initial state within a time, within a predefined time. So when we draw a state diagram, we usually use a function table to describe what it does. We simply use model function diagram, as we have discussed in previous lesson. Here the model name is vending machine control unit. We have inputs and outputs. Nickel and dime are inputs, so they simply signals that the nickel has been deposited or dime has been deposited. Outputs are reset and vending. So if we deposited 25 cents, and then this simply creates a signal to dispense a candy. So the functionality is simply the state diagram that we have described in previous slide. So if we have a model that may be represented by a state diagram in our design, then we can create such a function table and describe that model with inputs and outputs, as well as the functionality, where we simply draw our state diagram. The next modeling language is flowchart. It's usually used to describe a process or an algorithm. Its steps and control units. It's quite simple, and then it makes them accessible to a wide users. Wide range of users, as this simple. Here, as you can see, there are some symbols to be used in constructing flowcharts. We have a terminator, that's an oval, usually represented by an oval. General process is represented by a rectangle. If we have another flowchart that is used in our flowchart, what we call elaborated process, we use a rectangle with some with double slides, and we have decision symbol, that's a diamond, and The data manipulation can be represented by these four symbols: general data, stored data, displayed data, and direct data. So somehow we can combine this logically to represent an algorithm or a process. This is the most common modeling method that we use in electrical engineering. Here's an example: light monitoring system. That's an embedded computer system that monitors the light level of the environment. We have terminal symbols right here, start and end. And we have the sample light strength. So that's data processing. And then we have storing process. We store the sample in an array. And then we have an encapsulated or elaborated processing again. So this goes to another flowchart where we simply implement averaging. Then we have 1 millisecond wait, and then we display the data. So data display unit. And finally, we have a decision stage, depending on the response or the key press here. If it's pressed, and then we end the process. So we can then construct a function table for this data logger. We have inputs: light intensity, ambient light intensity within the environment, key press, user request to abort the data logging, and outputs: terminal, disk, where we store the report of light intensity. And the functionality simply presents the flowchart we have shown in previous slide. Okay. The next is Unified Modeling Language, UML. That is quite common in especially computer engineering, but we as electrical use this frequently as well. That is based on object-oriented software design process. It's a very valuable tool that can be applied to many types of systems, so all design processes. That's not limited. Programming or software. We have 6 different system views in this modeling language. That's why we call unified. All together represents this system with this object-oriented approach. Here, we're going to study 4 such system views. We'll skip the 2 systems. We have a scenario here. We consider Getter, which is an ultra-fast home delivery platform. You may have used this. You may use it. It's founded in 2015, and it was the second decacorn of Turkey. You might be familiar with this verse. Unicorn represents startups with a valuation of $1 billion, while decacorn represents startups with a valuation of $10 billion. So Getter is the second decacorn of Turkey. And here in UML example, as UML example, we'll consider V grocery in Getter. We imagine that there is a grocery virtual grocery in Getter and would like to use this grocery to represent UML modeling or system view concepts. Okay, the first view, system view, is static view, or simply characterized by class diagram. The intention of static view is to show the classes in a system and their relationships. Simply, static view is characterized by class diagrams. Okay, in object-oriented design, we have classes, and simply a class is a template for creating objects, and object is a particular instance of a class. So human could be a class, and Ali Kara would be an object, so a particular instance of human. When we compare object-oriented design and functional design, functional software design, OOD and OOP, we simply use objects instead of functions, and objects represent data and methods. So methods corresponds to functions, software, while data corresponds to attributes. Attributes corresponds to data in software design. Here you can see an example by considering we grocery, then we can create a class customer, and we have class label here, customer, attributes, name, address, and customer ID. So any object, any person can be described by name, address, and customer ID. There may be methods, change address, and here customer could be anyone who wants to order from the grocery of Getter. So we have interaction between the classes. Diagram, we'll be seeing that these interactions might be different. If one class is a subset of the other classes or another class, then there is a generalization relationship between the classes. If a class is composed of members of other classes, then we have a composition relationship. And if one class sends message to another, message from another, association relationship. So these three relationships should be somehow represented in class. Here is a class diagram for the grocery of Getter. Here, as you can see, we have one delivery, customer, grocery cart, order, and item. All of them are classes we have considered here. For delivery, we can see the attributes, and for customers, the attributes and the methods. So for grocery cart, also we can see 3 attributes and 1 method. For order, we have 2 attributes and 1 method. For item, we have 3 attributes and 1 method. So there is either one-to-one relationship or one-to-many relationship. We define cardinality for this, and we also show which class is how related to others. So delivery is sent to customer, customer receives delivery, and there may be one or many relationship here. The star represents many. And delivery orders sent by delivery, and delivery contains orders. So there is one-to-one relationship. And item and orders, as you can see, grocery cart is one-to-many here. So we can construct class diagram for any object-oriented modeling system. The next one is, next UML view is use case view. It shows the behavior of the system from user point of view. It's characterized by use case diagram, and here you can see use case diagram for V grocery of Getter. Here we have actors and use cases. Actors are simply clerk, customer, database, which are shown by some stick figure people, as you can see, stick figure people. And we have use cases represented by assemble order here, ovals. So order and delivery could be use cases, as we said, database, web server, clerk, delivery, customer. Each of these is an actor. So we can see the interaction from customer to deliver orders. So actor to use case, actor to use case, customer to web orders, or database to web orders. We can construct function table for this, for example, web order use case. Previous slide, so this one. We have customers, database, and web servers as actors, and this use case occurs when a customer submits an order via the web server. If that's a new customer, then there's going to be an account created. So customer information will be stored in the database as a new customer or new entry. If we talk about an existing customer, then we may simply update the. So customer order via the grocery cart. So that's the stimulus. So the response is verify payment, availability of order items, and if successful trigger, the assemble order use case. So that's the next use case if the response is positive. The next system view is state matching view, characterized by state diagram. We have already shown state diagram in previous slide. If we have a system with memory, then the diagram here you can see an example. State diagram for the V grocery customer login in Getter. So when a customer tries to log in to the system, then simply in this process represented by this state diagram. I'm sure that many of us are quite familiar with registration or login process. The next one, the last modeling language of UML, activity view. That is simply sequencing of activities needed to complete a task. So we have task and we describe the activities in order to complete a task. It's somehow related to use case diagram because tasks elaborated are individual use cases that can be identified in a use case diagram. Activity diagram can express the concurrent nature of task. We have symbols, force symbols, basically, ignoring the start and end, so terminators, states, transitions, forks, and joins. Here, you can see activity diagram for ordering, processing, and delivery for the Grosserov getter. We initiate the order. We have a fork here. There are two channels, two things that should be implemented concurrently. One is simply scheduling of the order. The other one is implementing this order or completing this order. We post the delivery and then put a schedule, the delivery route, and then collecting the order. In parallel with this, we post the clerk and then assemble order and send items. So together, joins here, and then we implement, so run the delivery. Okay, so we have discussed UML and 4 system views in UML out of 6. As we said earlier, there are 6 system views in UML, 4 of them. These are static view, diagram, use case view. We use use case diagram, and state mentioned diagram, activity view, activity diagram.